Welcome back to the Deep Dive. Today we're getting into some of the most complex, most specialized, and frankly, some of the most expensive engineering on the entire planet.
We really are.
Industrial air pollution control. We've been digging through technical documentation, chemical diagrams, operational notes, all the stuff that explains how these massive stationary sources, power plants, cement factories, refineries, stop their emissions from ever reaching the atmosphere.
It's a hidden world of engineering.
It is. And the news loves to talk about air pollution, but it's almost always focused on the what.
Right. The sulfur dioxide, the nitrogen oxides, the tiny particles.
Exactly. So our mission for this deep dive is to get into the how. We want you to walk away from this really understanding the intense kind of silent engineering battle that's being fought every single day inside those colossal smokestacks.
And if we connect this to the bigger picture, that fight against industrial pollution is, at its core, an engineering trade-off.
A trade-off. How so?
It's this constant battle. On one hand, you're trying to maximize efficiency. You want to catch the smallest, most elusive molecules and particles.
Okay.
But on the other, you have to minimize cost and maintenance. You're managing incredibly high temperatures, corrosive gas streams, and just the sheer volume of material moving through these systems.
So you can't just, slap a filter on a smokestack and call it a day?
Oh, not at all. Industrial exhaust streams are massive. They can be hundreds of degrees Celsius. They're carrying these complex chemical cocktails. It's a brutal environment.
That's really the conflict that drives everything we're going to talk about. And so the first thing any engineer has to do is separate the problem into two very distinct groups.
Right.
You've got the invisible chemical stuff, the pollutant gases.
Yeah.
And then you have the tiny solid or liquid bits, what we call particulate matter, or PM.
And we'll start with the gases because they require either chemical or thermal solutions.
Yeah.
Our sources organize these methods into what they call the AAC approach.
AC. Okay, what's that?
It's absorption, which is the wet cleanup, then adsorption, the dry capture, and finally combustion, which is just the final destruction method.
Okay, let's unpack this. Let's start with the first A, absorption.
The wet cleanup.
This is the idea of using a liquid, usually water, right? Or sometimes a special solvent,
Correct.
to literally wash the pollutant gas out of the airstream. It sounds so simple.
It does. It sounds like you're just running dirty air through a giant shower.
Exactly. But at the molecular level, it's a really demanding multi-step process. Mass transfer, they call it.
That's the term. And for the gas to actually move from the air phase into the liquid phase, three very distinct steps have to happen. If any one of those steps fails, your $1,000,000 scrubber is essentially just making the air wet.
Okay, so what's step one?
First, you have the diffusion of the pollutant gas to the liquid surface.
Okay.
So imagine this gas stream is just roaring past the liquid. The pollutant molecules have to physically break away from all that turbulence and get right up to the boundary layer of the liquid.
It sounds like trying to dock a boat on a riverbank that's moving at high speed.
That's a perfect analogy. They have to actually make contact.
So they've touched the liquid interface. What's step two?
Step two is the transfer across the gas-liquid interface. We often call it dissolution.
Dissolucerate.
This is the moment the molecule crosses that molecular barrier and actually dissolves into the liquid. And this is all governed by the solubility of that specific gas in that specific liquid.
So some gases are easier to grab than others.
Much easier. Sulfur dioxide, for instance, is super soluble in water. Others might need you to mix a chemical reagent into the water just to encourage them to make that jump.
Okay, and then the final step, once it's in the liquid, you don't want it just sitting on the surface ready to escape again.
Precisely. That's the third and final step, the diffusion of the dissolved gas from the interface into the bulk liquid.
So it has to move away.
It has to move away quickly.
Yeah.
You need to keep the concentration low right at that boundary layer, because if the concentration builds up too high near the surface, the liquid gets saturated right there, and the whole absorption process just stops cold.
So the efficiency all comes down to constantly refreshing that liquid boundary.
Yes. Maximizing that constant movement.
So the whole engineering challenge is just designing a structure that gives you the most surface area and the best flow path to make those three steps happen.
That's it in a nutshell.
Okay.
And our sources describe two really critical configurations for doing this. Towers, which use a thin film of liquid, and spray chambers, which use droplets.
Let's start with the towers, the thin film approach.
Okay, so towers and columns, these are built for just sheer efficiency and mass transfer. And we see two main types.
Yeah.
You have packed towers and you have plate towers.
What's a packed tower?
In a packed tower, the main shell is just filled with all this specially shaped random packing material. It could be ceramic saddles, little plastic rings, metal pawl rings, anything designed to provide a massive, massive wetted surface area.
Okay, so you have all this material inside.
Right. And the liquid flows down over this packing in a thin film while the dirty gas is forced to flow up against it.
Countercurrent flow.
Exactly. That countercurrent flow, plus the enormous surface area, it just optimizes the diffusion and dissolution steps. It gives the gas the maximum possible exposure to the scrubbing liquid.
And the other type, the plate tower, is a bit different.
Yeah, a plate tower relies more on collision and turbulence.
How does that work?
It uses these trays or plates spaced all the way up the column. The liquid pools on each tray,
Okay.
and the incoming gas is forced to bubble up through the liquid through little holes or caps. This creates a really churning, turbulent froth.
So a lot of mixing.
Intensive mixing. And then the liquid moves down to the next tray through something called a downspout. The whole goal is just bubble formation and contact.
So if I'm designing a system and gas removal efficiency is absolutely everything, I'm going to choose one of these towers.
You would.
But there's a huge catch, a really critical limitation.
This is the big one. This is the operational constraint you always have to remember. Towers, and especially the packed towers, are very easily plugged by particles.
Ah.
If you introduce a dusty, particulate-laden gas stream into one of these, the solids are just going to accumulate in that packing material, or they'll clog the downspouts on the plates. The whole system just locks up.
So they're only good for gas that's already clean of dust.
Generally, yes. The gas has to be extensively pre-cleaned.
So if my gas stream has both gas and dust, I can't use the best tool for the gas removal part.
It's a major engineering compromise.
And that's where the spray chamber comes in, using droplets instead of a film.
Exactly. Spray chambers and open spray towers, they offer you versatility. In these, the liquid is pumped through nozzles to create this vast cloud of tiny droplets, and the gas just passes through the cloud.
The trade-off seems pretty immediate.
It is. Spray chambers are just less efficient at absorbing gases than a packed column.
Why is that?
Because the contact area is shorter, the exposure time is much less intimate. It's just not as thorough.
So they're less effective at their main job, but they must have some massive secondary advantage.
They do. Their key selling point is that they remove both gases and particles.
Oh, okay.
The high velocity of the gas causes the particulate matter to collide violently with those liquid droplets, and the droplets then carry the particles right out of the airstream.
So it's the versatile compromise. You use it when the gas stream is too dirty for a packed column.
That's exactly it.
Okay, let's zoom out a bit and just look at wet scrubbers in general. They seem incredibly useful for a couple of reasons that aren't even chemical, like handling high temperatures and minimizing explosion hazards.
That ability to handle high temperatures is absolutely crucial.
Yeah.
A lot of industrial processes generate exhaust that's hundreds of degrees that would just melt or destroy dry filters or catalysts. Water instantly cools the gas stream. It acts as a quench system. Right. And by cooling the gas and adding all that moisture, you also significantly reduce the risk of explosion, especially when you're dealing with flammable things like volatile organic compounds, VOCs.
But the financial and logistical trade-off here seems staggering. It really ties back to that central conflict you mentioned, cost versus efficiency.
Oh, they are notoriously expensive to operate.
Really?
The initial capital cost for a basic scrubber might seem low, but your long-term operational costs are very high. You're dealing with a continuous need for liquid, the energy to pump millions of gallons of it against the gas flow, and just constant maintenance against wear and tear.
And the physical damage inside must be relentless.
Well, think about the environment inside one.
Yeah.
It's high temperature, high moisture, and you often have corrosive chemicals like hydrochloric or sulfuric acid being formed inside the scrubber.
Wow.
So that leads to severe problems with erosion and corrosion. You have to use expensive specialized alloys or, fiberglass reinforced plastic materials just to build the thing.
And what about dust?
You also have constant dust buildup, which requires regular, intensive washdowns. It's a maintenance nightmare.
But the biggest logistical headache isn't even the scrubber itself, is it? It's what comes out the bottom.
That's the primary downside of any wet cleanup. The pollutant isn't destroyed.
Right.
It's just transferred from the air into the liquids. So now you have these massive volumes of contaminated scrubbing liquid and eventually this final wet sludge.
So you've just created a new problem.
A huge one. You have to treat all that liquid and then you have to dispose of the resulting solid waste safely. For large operations, this sludge disposal requires dedicated handling sometimes specialized rail transport. And that just drives the long-term operational cost through the roof.
And visually, you have this white plume issue, which I think is a great analogy for an imperfect solution.
The white plume, yeah, it's the visible water vapor that remains after you scrub a hot saturated gas.
But the air is clean, right?
The air is chemically cleaner, yes. The SO or the PM has been removed. But the vapor plume itself can have an environmental consequence.
How so?
Under certain cool, moist atmospheric conditions, that vapor can lead to thermal inversion. It can essentially blanket a nearby area with moisture or even trap residual ground-level pollutants.
So it's a clean stack that still creates a visible and potentially disruptive environmental effect.
That's a good way to put it.
Let's use a critical application example to really nail this down. Flue gas desulfurization, or FGD. This is used mostly to scrub SO from coal plants, right? This is where these massive wet scrubbers are indispensable.
FGD is the benchmark of large-scale absorption. Often, the system uses a spray tower scrubber where the scrubbing medium isn't just water, it's a limestone slurry.
Limestone, so calcium carbonate.
Correct. And as the SO gas passes through that spray, it reacts chemically with the limestone to form gypsum, which is calcium sulfate.
So the whole point is to turn the pollutant gas into a manageable or even marketable solid.
Precisely. And this process requires these incredibly powerful recirculation pumps to constantly spray and move the slurry. And crucially, an oxidation air supply to complete the chemical reaction and produce the gypsum.
And what's at the top of the tower? You don't want that slurry escaping?
No, you have to have a mist eliminator. It's a series of baffles or vanes to make sure those fine liquid droplets don't escape. It prevents carryover of the corrosive slurry or residual water.
And the end product is what?
Well, it's either dry gypsum, which can often be sold to wallboard manufacturers.
So a useful byproduct.
Right. Or if the process is less complete, you just end up with this nasty, wet calcium sulfate sludge that has to be landfilled.
And the whole process just sounds like it consumes colossal amounts of energy and water.
It does. It's an overwhelming set of compromises. If your gas stream is high volume, high temperature, and full of OROs, the wet road is pretty much the only way. But you are immediately committing to years of high operating costs and massive waste disposal issues.
It's a tough reality. And what about the low-energy scrubbers that the sources mentioned, like a gravity-settling chamber scrubber?
Yeah, those rely on much, much simpler mechanisms. They basically just expand the volume of the gas stream to slow it down.
Yeah.
And that allows gravity and inertia to settle out the very coarsest particles, we're talking bigger than 10 micrometers, as the gas hits a simple water spray.
So they're not for high efficiency?
No, they're often just used as a first stage, a pre-cleaner to protect the more sensitive, high-efficiency equipment downstream, like a packed tower.
And you can boost that simple mechanism with an impingement plate design.
Yes. In that design, the gas flow is forced through these small orifices that are covered by a thin layer of water.
Okay.
And the energy of the incoming gas flow actually atomizes the water at the edges. It creates these small, highly reactive droplets.
So it's using the gas's own energy.
Right, to create the scrubbing medium. This enhances particle capture through direct impaction, so it's more effective than a simple spray, but still, significantly less efficient than systems designed purely for fine particles.
So if absorption is the complex, costly, wet sink route, let's pivot to the second A, absorption.
The dry capture.
Instead of dissolving the gas into a liquid, here we're bonding it to a solid.
Adsorption is often a much cleaner solution, but it's far more limited in its application. Here we're talking about mass transfer, where the pollutant gas, the adsorbent, physically or chemically bonds to the massive internal surface area of a porous solid.
The absorbent.
The adsorbent, yes. The gas literally penetrates the pores of the solid and just sticks.
Which means you need a very specific kind of material for this. You need a sponge, basically, but one with an impossibly large internal structure.
That's the key requirement for any effective industrial adsorbent. An enormous active surface area per unit volume.
How enormous are we talking?
We're talking about materials where a single gram might have a surface area equivalent to a football field. It's all because of microscopic porosity.
And the way the gas sticks can vary, can't it?
Yes, there are two main mechanisms. There's physical bonding, which is weaker. It's based on simple van der Waals forces or electrostatic attraction. The gas molecules are held kind of loosely and can be easily released.
Okay.
And the other is chemical bonding, or chemisorption. That involves an actual chemical reaction which creates a much stronger, often irreversible bond between the pollutant and the solid surface.
What are the main industrial adsorbents that are used for this?
The standard workhorses are things like activated carbon. It's prized for its huge surface area, and it's used to capture organic vapors and hydrocarbons.
Okay.
Then you have molecular sieves, which are engineered porous crystalline materials, silica gel, and activated alumina. They're all deployed to capture pollutants like HERO, SAO, NO, that kind of thing.
This method seems ideal. I mean, no liquid waste, high efficiency, but here comes the critical constraint, the thing that limits its use compared to wet scrubbers.
The presence of water.
Water.
It is the single largest operational hurdle. The gas stream has to be virtually free of moisture for the adsorbent material to work properly.
Why is that?
Because adsorbents are nonspecific, they love water vapor. If the gas stream is wet, the water molecules will immediately rush into the pores and they'll preemptively saturate all the active sites, basically pushing the target pollutant molecules out of the way.
So in many industrial exhaust streams, the high moisture content just renders adsorption completely useless.
Unless you employ expensive pretreatment, like gas drying.
Which brings us right back to high cost, just in a different part of the process.
Exactly.
And the second major challenge is managing the material once it's full. This concept of breakthrough.
Breakthrough is the operational failure point. That solid adsorbent bed has a finite capacity. Once the gas starts passing through without being captured because all the active sites are full, the pollutant breaks through to the clean side of the system.
And your environmental compliance is gone.
Instantly.
So what's the solution when breakthrough happens?
It forces a very energy-intensive second step. You have two choices. You can dispose of the material, which is environmentally and financially costly because you're throwing away a valuable substance, or you can do regeneration. Regeneration involves heating the bed to a moderately high temperature, often using steam or a vacuum, to release the captured pollutants from the pores.
But that requires a ton of energy.
A significant input of energy. And then that released pollutant gas is usually sent to a secondary treatment system, like a combustion unit, to finally be destroyed.
So adsorption is often just a capture and hold method. It still requires another step and more energy for the final destruction.
Precisely. The lower capital cost has to be weighed against the persistent, significant energy cost of those regeneration cycles. It's an intermittent cleanup system, not a continuous one.
Okay, so if the wet route is complex and messy, and dry adsorption is limited by moisture and capacity, sometimes the only answer is just brute force destruction.
That brings us to C, combustion.
Let's talk about combustion.
Combustion, or incineration, is conceptually the simplest method. You just completely oxidize the pollutant gases, things like carbon monoxide, various hydrocarbons, by exposing them to high heat.
And you convert them into harmless products.
Benign products like coeuro and water vapor. It is permanent destruction.
The choice between the two main types of combustion seems to depend entirely on the energy concentration of the dirty gas stream itself. There's this threshold, 3.7 megajoules per cubic meter.
Absolutely. That number is critical. If your pollutant stream has a high energy concentration greater than 3.7 mgm, you use direct flame combustion or thermal incineration.
What does that mean?
It means the stream is rich enough in burnable hydrocarbons that once you start the reaction, it sustains itself. You don't need to add any auxiliary fuel.
So the pollutants actually become the fuel source for their own destruction.
Exactly. The exhaust gases are pushed into a combustion chamber. They're held at extremely high temperatures, often over 750 degrees Celsius, for a specific residence time to ensure complete oxidation.
The equipment sounds relatively simple.
It is just a burner and a chamber, but their requirement is strict. The final oxidation product must be non-toxic.
And what kind of industrial processes create streams that are rich enough to sustain this?
These are applied to high concentration emissions, things generated by, say, industrial solvent cleaning processes, some textile finishing, varnish cooking, and even meat smokehouses, where the VOC concentration is high enough to be energetically valuable.
Okay, now what if the concentration is lower, which I imagine is often the case for high-volume streams?
It is.
You can't afford to heat millions of cubic meters of air to 800 degrees just to destroy some trace pollutants.
That's where catalytic combustion or catalytic incineration comes in. This is the solution for streams with energy content below that 3.7 mgm threshold.
Right, because your fuel bill would be crippling otherwise.
It would be. So the trick here is to lower the necessary reaction temperature.
You do that with a catalyst.
We achieve this by introducing a catalyst bed. The catalyst is typically an expensive metal like platinum, palladium, maybe rhodium, and it's supported on a ceramic lattice or a honeycomb structure.
And it just helps the reaction along.
It chemically assists the oxidation process. It allows the reaction to happen efficiently at much lower temperatures, usually between 300 and 500 degrees Celsius.
Which translates directly into massive savings on supplemental fuel.
Huge savings.
Wait a second, if catalytic combustion is so much cheaper to run because of the lower temperatures, why would anyone ever use direct flame combustion?
That is an excellent question, and it highlights the trade-off perfectly.
Okay.
While catalytic combustion saves you a ton on fuel, it introduces severe maintenance risks. The equipment for direct combustion is robust, it's simple, it can handle extreme conditions.
But catalytic incinerators are fragile.
Very fragile when it comes to contaminants.
And that fragility is the major vulnerability. Catalyst poisoning.
It is the Achilles heel of the entire system.
So what poisons it?
Contaminants in the gas stream, especially sulfur compounds, phosphorus, heavy metals, lead, they can physically coat the catalyst surface or they can react chemically with that expensive metal, rendering it inert.
So the catalyst just stops working.
Its efficiency plummets, and you have to shut the whole thing down and incur the huge cost of replacing the entire catalyst bed.
Wow.
The risk is so high that if a gas stream is known to contain these specific contaminants, direct flame combustion is often the only economically feasible option despite its high fuel cost, simply because it's reliable and robust.
That really puts the cost of compliance into perspective. You're either paying an enormous energy bill for guaranteed destruction, or you're betting on a lower energy cost system that risks a catastrophic failure requiring a multi-million-dollar replacement.
It forces you to do rigorous pretreatment of the gas stream just to protect the catalyst.
And where do you see catalytic incineration used most?
It's heavily applied to emissions from things like printing presses, which have low concentration VOCs, and in specific applications in asphalt oxidation and chemical manufacturing where the streams are generally pretty clean, but they're low BTU.
We've spent a lot of time on the chemical and thermal solutions for gases. Now let's pivot entirely. Let's go to particulate matter PM.
The physical stuff.
The physical solids and liquid droplets suspended in the air. And this requires a total shift in engineering focus from chemistry and heat to pure physics and mechanical force.
We're moving from molecular dynamics to macro-engineering forces. The mechanisms we rely on to capture PM are all fundamental physical principles.
Such as?
Gravity settling for the big, heavy particles, inertial force for moderately sized ones, filtration or sieving for the fine stuff, electrostatic attraction, and even deliberately enlarging particles to make them easier to capture.
The core challenge here seems to be particle size. I mean, the difference between a 10 micrometer particle and a 0.5 micrometer particle must be exponential in terms of engineering difficulty.
That's the crux of the PM issue. The smaller the particle, the less mass it has, and the more it just behaves like a gas molecule. It gets randomly pushed around by air currents, Brownian motion, rather than following gravity or inertia.
So you need tailored solutions for each size class.
Exactly.
Let's start with the first line of defense, the industrial workhorse for the core stuff, the cyclone.
The cyclone.
How does that principle of centrifugal force translate into industrial-scale cleaning?
It's really elegant in its simplicity. The particle-laden gas enters the cylindrical chamber tangentially, so at an angle.
Okay.
That inlet orientation converts the horizontal momentum of the gas into this powerful, high-speed vortex, forcing the gas stream to spin rapidly around the chamber wall.
What happens to the particles in that vortex?
Because the particles have mass and inertia, they're subjected to a massive centrifugal force. It's the same force that pushes you to the outside wall on a high-speed carnival ride. And that force flings the heavier particles outward. They impact the inner wall of the cyclone, they lose their velocity, and then they just settle via gravity down the conical section at the bottom into a hopper.
And the clean air.
The cleaned air spirals back up through an inner tube called the vortex finder and exits the system.
This mechanism is why the cyclone has such a severe efficiency limit, right? It's great for certain things, but useless if you're dealing with very fine emissions.
Absolutely. Cyclones are inherently inefficient for anything small. They're highly effective only for coarse particles, so generally things larger than 10 micrometers.
What about the really small ones?
Any particle that's 1 micrometer or less just does not have enough mass or inertia for the centrifugal force to overcome the drag force of the airstream. Those fine particles just follow the air vortex right out the clean air exit.
So if you're running a sawmill and dealing with wood chips, a cyclone is great.
perfect.
But if you're trying to clean ultrafine fly ash from a boiler, a standalone cyclone is going to fail your compliance regulations every time.
Every single time.
But they are indispensable because they're cheap and they're robust.
Their main benefits are their simplicity, low initial capital cost, and minimal maintenance. There are no moving parts to break, no filters to change, and they can handle high temperatures and abrasive material without much of an issue.
And for high throughput?
For higher throughput, we use multi-cyclones. That just involves running the gas through several smaller parallel cyclone units. The smaller cyclones generate a tighter vortex and a higher separating force, so it marginally improves efficiency for slightly finer particles while still handling the overall volume.
And you find them everywhere. Cement production, refineries, even just simple dust removal and grain handling.
They are the essential pre-cleaner to protect the more expensive, more sensitive equipment that's downstream.
So if the cyclone is the coarse workhorse, the baghouse, or fabric collector, is the high-efficiency PM specialist. This is where we use physical filtration for the really fine stuff.
The baghouse is truly the industrial version of a vacuum cleaner. It forces the particle-laden gas through hundreds of these large tubular fabric bags, and they function as physical sieves.
And this gives you excellent control.
Excellent control for fine particles. You often achieve efficiencies above 99% for particles that are smaller than 5 micrometers.
How is that extremely high efficiency achieved? Is it just the fabric itself doing the work?
It's a combination of mechanisms. I mean, yes, there's the initial sieving and screening by the individual fibers,
Okay.
but 3 other factors are crucial. First, you have interception by the fibers, where a particle's path just brings it too close to a fiber and it sticks.
And second,
And this is the most important part, is the development of the dust cake.
the dust cake. I imagine that once that sticky layer forms, you just have to shut the whole thing down. That sounds like a nightmare.
It sounds like a problem, but the dust cake is actually beneficial up to a point.
Really?
That layer of collected dust on the outside of the bags, that becomes the primary filter medium. It fills in all the large spaces between the woven fibers, and it achieves a much superior filtration efficiency than the fabric could on its own.
Why?
However, as that cake thickens, it dramatically increases the pressure drop across the filter. That means the fans have to work harder and harder, consuming vastly more energy.
So it necessitates constant controlled cleaning.
It does.
And the material science for those bags must be intense, given the heat and chemistry involved.
Oh, absolutely. The bags can be massive, up to 10 meters long and 1/3 of a meter in diameter.
Wow.
And they're made from specialized natural or synthetic fibers like fiberglass, Nomex, specialized polyesters, all chosen specifically to resist the high temperatures and the chemical attack of that particular exhaust stream.
So how do you manage the cleaning without a full shutdown?
Engineers have devised some really sophisticated periodic cleaning methods. One common method is periodic power shaking, which just physically vibrates the bags to dislodge the cake.
Okay, that's pretty straightforward.
A more modern and effective method is the reverse pulse jet system. This involves a blast of compressed air that's shot down the inside of the bag.
What does that do?
That pulse momentarily inflates and reverses the fabric, and it just shatters and drops the dust cake into the collection hopper below. And this is often done segment by segment, while the rest of the baghouse stays operational so you get continuous cleanup.
And the applications for baghouses, they must cover every industry that generates fine, dry particulate.
They do. Key applications are things like cement manufacturing, where you have huge volumes of fine dust, carbon black production, managing flue gas from boilers.
And they're in our daily lives, too.
They are. The technology is scaled down and used as diesel particulate filters, or DPFs, in trucks and buses to clean up soot particles.
Okay, now we have to circle back to a wet method, but one that's used primarily for particulate control. The Venturi scrubber.
Yes, the Venturi is an interesting hybrid. It uses liquid to capture extremely difficult to manage fine particles, often those under 1 micrometer, where baghouses and cyclones really struggle.
So what is it about the Venturi geometry that makes it so uniquely suited for this high-energy fines capture, as opposed to just a simple spray tower?
It is all about focusing kinetic energy. The Venturi is an hourglass shape. It has 3 sections, a converging entry, a very narrow throat section, and a diverging exit.
All right.
The dirty gas accelerates rapidly as it goes into that converging section, and the scrubbing liquid is introduced, usually right at or just before the throat.
So the energy of the inlet gas stream itself becomes the atomizing mechanism for the water.
Exactly. The extreme velocity of the gas stream, it can reach speeds up to 300 feet per second. It violently atomizes the scrubbing liquid into this dense fog of tiny droplets right in that narrow throat.
And that throat becomes a bottleneck of violent collision.
That's a perfect description. Because the droplets are moving relatively slowly compared to the gas and the particles, you get this massive relative velocity. And that causes the small liquid droplets to effectively scavenge the fine particles through forced impaction.
That sounds like a massive energy sink. You must be putting a lot of fan energy into the system just to drive that capture mechanism.
You are. Venturi scrubbers are classified as high-energy scrubbers for precisely that reason, the necessary pressure drop created in the throat. You are essentially trading enormous operational energy costs from running powerful fans for extremely high collection efficiency of the fines.
What happens in the third section, the diverging section?
As the gas leaves the throat and enters that diverging section, it slows down and the pressure recovers a bit.
Okay.
Critically, this slowdown allows for cooling and expansion, which can trigger the condensation of water vapor around the captured particles. And that phenomenon is hugely important. It actually makes the particle larger. It grows a water jacket. And that significantly aids its capture in the downstream separation system.
So it's not just a collection device, it's also a particle enlargement device.
In a sense, yes.
What kind of applications absolutely require this level of high-energy intervention?
It's the ideal technology for removing wet, corrosive, and ultrafine particulates. It's also superb for processes that generate extremely hot gases because it gives you that immediate quenching.
Right.
So key applications include SO scrubbing, using seawater or lime, and handling difficult chemical process exhaust streams where the particles might be sticky or highly corrosive.
And for the absolute ultimate efficiency.
The ideal setup for maximum fine particulate control is pairing the Venturi scrubber with the downstream cyclone or impinger system.
How you combine them?
You combine them. The Venturi handles the violent particle capture and the droplet enlargement, and then the downstream cyclone easily and efficiently separates those now enlarged water-laden particles from the clean gas stream.
That combination is often cited as the best technical solution for high-efficiency, high-volume fines removal.
It is.
Okay, let's move to the last major PM control technology. This one requires neither a physical filter nor liquid droplets, the electrostatic precipitator, or ESP.
The ESP. It's entirely based on electromagnetic force, which makes it a highly efficient dry removal method.
This is truly an electrical cage match designed to clean the air.
That's one way to put it. The core principle is simple. You induce an electrostatic charge on every particle, and then you use a massive electric field to pull that charged particle toward an oppositely charged collector plate.
Which means the entire design is dictated by a physics equation, F equals leak.
Q.
Explain how that principle is engineered at an industrial scale.
F eq Q. It tells us that the force, F, pulling the particle is the product of the electric field strength, E, and the electrostatic charge on the particle, Q.
So to get a strong enough force.
To generate a strong enough force to yank a tiny particle out of a high-volume gas stream moving at, say, 50 miles per hour, you need a colossal electric field, an enormous E.
And that's why ESPs operate at these staggering voltages.
Right, typically ranging from 30,000 to 100,000 volts DC.
That's astonishing. Walk us through the operation of the chamber itself.
Okay, so as the dirty gas enters, it passes through an electrical field that's established between two main components.
What are they?
In the center, you have the negative discharge electrode, or the corona electrode. This high voltage ionizes the gas molecules. That creates the corona discharge. And as the particles pass through this highly charged zone, they pick up a massive negative charge.
So now you have negatively charged dust flying through the system.
Correct. And these negatively charged particles are then immediately subjected to this powerful electrostatic force pulling them toward the surrounding collecting plates.
Which are positively charged.
Usually grounded, which makes them effectively positive relative to the electrode. And the force is so strong that the particles accelerate and they stick firmly to these plates, forming a layer of dust.
And because it's a dry system, how do you handle collection once the plates are all covered?
The material has to be removed periodically. This is often done through a mechanical process called wrapping. Yeah. Automated wrappers or vibrators periodically strike the collecting plates, and that causes the collected dust layer to suddenly just fall down into hoppers below. And this all happens without shutting down the gas flow.
What is the application niche for the ESP? I mean, what problems does it solve that other technologies can't?
Its main strength is highly efficient dry removal with minimal energy consumption from fans because the pressure drop across an ESP is extremely low.
Okay.
It can handle massive gas volumes and extremely high temperatures,
Yeah.
often requiring only minimal pre-cooling.
So that makes it a staple in industries that generate huge amounts of dry particulate at high temperatures.
Most notably coal-fired power plants for collecting fly ash and cement kilns. It's also the technology that's often cited for the efficient dry removal of household smoke and fine dust in residential airstreams.
We've now covered the full spectrum of industrial cleanup solutions, from chemical absorption to high voltage collection.
Mm.
But as we said at the start, none of this effort really matters if we can't prove the systems are working and that regulations are being met.
Exactly.
So the final essential piece of this whole puzzle is the engineering of measurement and monitoring.
Verification is paramount. These specialized tools are essential for regulatory compliance, for research validation, and for constantly proving the efficiency of the control systems we just discussed. In the world of environmental engineering, if you can't measure it, you can't manage it.
So let's look at how PM is measured out in the field. What devices are necessary to accurately sample airborne particulates?
For measuring airborne particulates, we use these very precise mechanical samplers that pull air through filters over a set period of time.
Okay.
These include the low-volume dust sampler, which gives you very precise but small samples for detailed analysis.
And the high volume one.
And the high-volume airborne PM sampler, or the HIVOL, that pulls a much larger volume of air through a big filter, which lets researchers collect enough material for a really comprehensive chemical composition analysis.
So you can find out not just how much dust there is, but what's in the dust.
Exactly. The concentrations of specific heavy metals or compounds within it.
And what about the invisible gases?
For gases, we rely on continuously operating instruments. These are often housed in dedicated mobile units or permanent structures we call ambient air quality monitors.
These are complex systems.
Very complex. They use techniques like non-dispersive infrared or chemiluminescence to continuously analyze gas streams for specific pollutants like NORs, NOGUROs, carbon monoxide, and ozone. They provide that real-time data to regulatory bodies, proving compliance day by day.
And the fascinating detail our sources provide is the sheer diversity of where this sampling has to happen. It reflects these global and regional pollution challenges.
That's right. To track localized exposure, we see PM sampling stations situated right on the rooftops of major urban centers.
Like the sites mentioned at Punjab University or King's College London.
Right. Those locations capture the immediate impact of traffic and localized industrial emissions on densely populated areas.
But conversely, to track long-range transport and broader atmospheric trends, you need to be somewhere remote and isolated.
Exactly. For broader atmospheric gas sampling, units are placed far, far away from local sources of contamination, like the atmospheric gas sampling station that's maintained at Whiteface Mountain in New York.
And what does a site like that tell you?
That site tracks regional pollutant concentrations. It helps scientists understand how far SO or NO Euros travels before it precipitates or impacts remote ecosystems.
So the data collected from all these disparate locations, it feeds directly back into justifying the design and the efficiency requirements for every single industrial control system we've talked about today.
It closes the loop.
This deep dive has really shown that cleaning up industrial emissions is so far from simple. It's a field that's built on constant compromise and really sophisticated engineering.
It is.
We've navigated the technical trade-offs between the energy-guzzling, sludge-generating wet cleanup of absorption and the moisture-sensitive, regeneration-costly dry route of adsorption.
We compared the high energy cost of direct combustion with the high catalyst risks of catalytic incineration.
And we've also seen how mechanical physics just dictates the PM solutions, from the centrifugal simplicity of cyclones for coarse particles
to the high-energy collision dynamics required in the Venturi scrubber for the ultrafines, and finally, that high-voltage elegance of the electrostatic precipitator.
Every time an engineer chooses a pack tower over a spray chamber or a baghouse over an ESP, they're weighing operational energy, maintenance complexity, and material compatibility against maximum collection efficiency for their specific problem.
It's a constant balancing act.
This raises an important question that, for me, summarizes the engineering challenge of the 21st century.
And what's that?
What is the ultimate environmental and energy cost of transforming air pollution into solid or liquid waste?
That's the one. Think about the circularity of pollution. We spend colossal amounts of energy running recirculation pumps and powerful fans, and then we capture the airborne pollutants into a solid form, fly ash, gypsum sludge, spent catalyst.
Right.
These systems clean the air, but they inevitably create these secondary pollution streams that still require safe disposal or energy-intensive regeneration.
So the remaining challenge for environmental engineers is designing systems that minimize that secondary burden.
Reducing the energy for fans and pumps, generating less sludge, creating more closed-loop systems. How will the necessity of managing these captured wastes influence the economics and design choices of future industrial systems, pushing us closer to truly zero-emission or zero-waste operations? That's the question that will define the next generation of industrial cleanup.
A profound challenge. It moves the focus from just the smokestack to the entire supply chain of waste. Thank you for joining us on this deep dive.